All right, so what if I give you two vectors though, and I ask you to come up with the cross product and I don't tell you the angle, right? Because so far, all we have right now is this, right? That A cross B is equal to the magnitude of A, magnitude of B, sine of the angle between them times n. So you need to know the angle between them. So what if I don't? So there is a way to compute the cross product without referencing the angle or the magnitudes. And here it is. Okay, so if I want to take the cross product of A1, A2, A3 with B1, B2, B3, then here's the formula here. You might think, okay, is that something I need to memorize? The answer is sort of. You have to be able to take a cross product of vectors in component form without writing down a formula like this. But I do not suggest memorizing this as you see it. Let me show you the technique that I would suggest you use. All right, so it goes like this. When you need to take a cross product, you're going to compute something called the determinant. Okay, that word at this point isn't too important. Some of you who've taken linear algebra will recognize it. So I'm not even going to get into that. Let me just kind of give you my personal method for doing this. Other instructors will show you different things, right? Your physics instructor might tell you something different. There's no right or wrong here. This is just different ways of thinking about how to do this. This one of my professors taught me when I was taking this same class, and he calls this the spaghetti method. All right, so what you're going to do is you're going to write ijk twice in a row, ijk, ijk. Then you're going to write the first vector in your cross product twice in a row, so a1, a2, a3, a1, a2, a3, and then the same thing with your second one below that, b1, b2, b3, b1, b2, b3, okay? And here's where the spaghetti part comes in. So this is called the spaghetti method, at least according to my old professor, because you kind of think of lying a spaghetti noodle across this. And so what you're going to do is in order to produce the I component of your cross product, you're going to start a spaghetti noodle here and let it go through A2 and B3. And then you're going to fold it around this way to B2, A3, and I. And so you're connecting up the I's with a spaghetti noodle. And so what that gives you is A2 times B3, and then you remember to subtract B2 times A3. Okay, so you're always going to put a minus sign in the middle. And then when it's time to do your J component, you do the same thing, but you connect up your J's with your spaghetti noodle. So JA3B1 connected up to B3A1J, and you put a minus sign between the reds and the blues there. And then same thing with the K's. Lay your spaghetti noodle down, A1B2 minus B1A2. And that's how you can get your I, J, and K components of your cross product. So don't memorize this. Lay out your vectors in this way, and then you'll be able to come up with it every time. So let's actually do an example here. All right, so example 3. All right, so we're going to take U cross V. All right, so our instructions were I, J, K, I, J, K. And then I'll write out 2/3, 1, 1/2, 2/3, 1, 1/2. And then 4, -6, 3, 4, -6, 3. Okay, so we have it all laid out like this. All right, so now I'm going to say U cross V is equal to, all right, and I'm going to switch my color here. So I'm going to start with my eyes, and so I lay down my spaghetti noodle. 1 times 3 minus -6 times a half. 1 times 3 minus -6 times a half. That is my I component, or my X component. All right, switch colors again here. Connect the J's. 1/2 times 4 minus 3 times 2/3. 1/2 times 4 minus 3 times 2/3. And then yet one more color here. So my K's. So my K will be 2/3 times -6 minus 4 times 1. 2/3 times -6 minus 4 times 1. And that's going to give me my cross product. So what do we get here? 3 plus 3. We get 2 minus 2. And we get -4 minus 4. So 6, 0, -8. Now, if you don't want to really write that much stuff out, that is perfectly understandable. So let me show you what you're going to do when you start to get comfortable with this and maybe want to take some shortcuts. So here's what I do, now that I've been doing this for a while. I just write out IJK. I don't write it out twice. And I still go ahead and go 2/3, 1, 1/2, and then I do 4, -6, 3. So the way to go about this, if you're not going to write it out this much, is you still start off the same way. You still go, right, 1 times 3 minus 6 times 1/2, and then you realize that as you go through here, there's nothing there, but it really comes to the other side like this. So, I grew up playing like, Mario Brothers and things like that on just the regular Nintendo system. And Mario Brothers wasn't like this, but there were games where if you ran out the right side of the screen, you would all of a sudden reappear on the left side, right? So, I realized that if you played video games, you were of a different generation than I am, but maybe you've seen something like that. So the idea is I'm running off the right side of the screen and I just end up coming back through on the left. And of course that still gives me this, right? And then for the J, right? So J times 1/2, but I'm off the screen, but where would I reappear? I'd reappear right here in the third row. And then what am I going to do? I'm going to end up with 3 minus 3 times appearing over here 2/3 J. Okay, and then you end up doing K as well, right? So I don't know, color green, I guess. K would be, okay, I am immediately off the screen. 2/3 times -6 minus 4 times 1 times K. So you'll just kind of get used to doing that, even though you can't see it all, you can kind of imagine it just reappearing on the other side, and so that's perfectly acceptable as well. So here's another example where we can use the cross product to help us solve a problem. So what they've done is they've given us 3 points, and yes, these points are in 3-dimensional space, but I would recommend let's not get too wrapped up in trying to graph them, in an XYZ coordinate system. Let's just go ahead and, just make a sketch, right? I'm not worried about accuracy here too much. Okay, so let's say here's my points, and I'm not, like I said, I'm not worrying too much about accuracy. So we'll go PQR. All right. Now, they want us to find this area. All right, so we're supposed to find that area. All right, now, if we want to find that area, let's think about what we've learned. We've learned that if we have a vector here, and we have a vector here, if we take the cross product of these vectors and take the magnitude, then it's going to give me the area of this parallelogram. Okay? Which is not what we're looking for, but we do know that it's exactly double what we're looking for. So if I let's call this one A and this one B, what I know is that the area of my triangle is going to be 1/2 the magnitude of the cross product of A and B. All right, so if I can just figure out what A and B are and take their cross product, I'll be good to go. But what we definitely can do is if you want to figure out the components of A, remember, all you have to do is subtract the terminal point and the initial point. So that means let's take P and Q. Q is our terminal point. So let's take 3 minus 1, right? So I'm taking this 3 minus this 1. 4 minus 1 and 3 minus 5. So that must mean A is the vector 2, 3, negative 2. And then the vector B would be R minus P. So that's going to be 1 minus 1, 5 minus 1, and 7 minus 5. So that'll be 0, 4, 2. And so then if I want to know what the cross product is, I, J, K, right? And I'll go ahead and write it out here. I, J, K. And so we'll put 2, 3, negative 2, 2, 3, negative 2, 0, 4, 2, 0, 4, 2. And so to compute A cross B, all right, spaghetti method, connect up the i's. So that tells me it's 3 times 2 minus 4 times negative 2. Connect up the j's, negative 2 times 0 minus 2 times 2. And then connect up the k's, 2 times 4 minus 0 times 3. Okay, so then we can clean that up. So our cross product is, so we got 6 plus 8, so we got 14, negative 4, and 8. But of course up here, what do we need? We need the magnitude of that, right? But we know how to compute the magnitudes of vectors, right? It'll just be the square root of 14 squared plus negative 4 squared plus 8 squared. And that's going to give me, well, actually I don't know exactly what that gives me under the square root. Didn't bother to write it out. 14 squared plus 16 plus 64. So under that square root, we get the square root of 276. So then over here, I'm going to say this is 1/2 times the square root of 276, which is approximately 8.31. So 8.31 square units is going to be the area of that green triangle. All right. So, we've been talking about what the cross product can do you know, and in large part, like that last example was in 2 dimensions, right? So this cross product is a 3 dimensional um, uh, thing that we compute. It only applies to 3 dimensional vectors. However, at the same time, um, it gave us information about just the area of a triangle. Okay, but we might wonder, like, can this apply to volume? All right, so this introduces what we call the scalar triple product. So the answer is we can also get the volume of, it wouldn't be a parallelogram, but it's called a parallelepiped, which is just, think it's a 3 dimensional parallelogram. We can find its volume by taking the dot product of one of the vectors with the cross product of the other two. Okay, so here's how this breaks down. First of all, if you have the area of this base here, so this is the A that they're referring to, and then you know the height of the parallelepiped, it makes sense that that would give you volume. So area times height. But we know area, right? Area is the cross product of B and C when you take its magnitude. So that's the area. Okay, now the claim is that this is the height. Okay, so let's see if we believe that. So here's the height. Here's the vector A. So if I make this angle right here, okay, the angle between, and remember the cross product is going to stick up like this, right, B cross C. So the area, the angle between the cross product and the vector A is theta. So the height then would have to be the magnitude of A times the cosine of theta, because it's this adjacent side here. All right, so that's why that's our height. And if you look at this, if you have the magnitude of a vector times the magnitude of another vector times the cosine of the angle between them, then what you're going to get is the magnitude of the dot product of those two vectors. The reason we have magnitude here, by the way, is because when you do a dot product, right, sometimes it can be negative. Well, this cosine's also in absolute values, so this is always going to be a positive quantity. All right, so that's called the scalar triple product. So let's look down here at example 5. So the claim is we can come up with the volume of this parallelepiped that you see right here. And the nice thing is it doesn't really matter which vectors you pick for which role. So what I'm going to do is I'm just going to take, so we're going to go absolute value of 2, 2, 1, dotted with the cross product of 1, 0, 3, and 0, negative 2, 0. All right, so over here, let's go ahead and do that cross product. IJK, IJK. So 1, 0, 3, 1, 0, 3, 0, negative 2, 0, 0, negative 2, 0. All right, so down here we can go ahead and write this out. So this is 0 times 0 minus negative 2 times 3 is going to be positive 6. I'm going to do this a little bit quicker. 3 times 0 minus 0 times 1 is 0. Maybe I should be writing this out here. 6, so that was 0 times 0 minus negative 2 times 3. This 0 here was 3 times 0 minus, what did I say, 0 times 1. And then my k is going to be 1 times negative 2 minus 0 times 0. so -2. So that's my cross product. So V is equal to 2, 2, 1, dotted with 6, 0, -2. And then the dot product compared to the cross product is real easy, right? 2 times 6 plus 2 times 0 plus 1 times -2, which is going to give me 12 minus 2. So that gives me a volume of 10 cubic units. In this section, we're going to learn how to work with the equations of lines and planes, look at their graphs, and do various problems involving both lines and planes. And we're going to start with lines. And so what we have to do at first is understand the idea of a vector equation. All right, so one of the things that you learn about in previous courses is how to write out a parametric equation. Okay, so here's an example of a parametric equation that you might have seen before, like x is equal to x0 plus at. Okay, where the idea is x0 and a are just constant numbers, and then t is your parameter value, and you let t be various things. And we can do the same thing for y and for z. Okay, so now to give a little bit more of a concrete example, in 2 dimensions, you might have had something like this. Okay, where the idea is you let t be different things, and then that sketches out a graph because it produces points in x and y, and so you get a graph, and this one turns out to be a line. So we want to take that same idea and expand it to 3 dimensions, but the way we're going to do it is we're going to express it as a vector. Okay, so it's the same idea over here, where this vector r is going to be x, y, z. This vector r0 is going to be x0, y0, z0. So just some initial vector. And then this vector v is going to be like this: a, b, and c. And so this is a vector equation that contains all the information that you would get out of a set of parametric equations. Okay, so it turns out that a line in 3-dimensional space can always be expressed this way, where r0, this is what we call the initial vector. Okay, so the vector when t is equal to 0. And then v is what we call the direction vector. All right, so here's how this works. You start off with r0. Okay, so that's this guy right here. So you start off with r0, and that is a vector pointing to an initial point along this line. And then you take your direction vector v, and this direction vector v needs to be going in the same direction as you want your line to go. Right? So if I kind of try to translate this up here, here's v. Okay. And then the idea is we are taking r0 plus some multiple of v. Okay, so if we multiply v by something, it either gets longer this way, or shorter, or it goes back in the negative direction if t is negative. But either way, what ends up happening is that you are taking this vector plus this vector, so this gives you another vector that goes from the origin to here, and that's your r. So in this case here, the v gets multiplied by something, extends all the way out, so this plus this gives you your r. Okay, so the way to think about a vector equation for the line, here's what helps me, is that the vector equation is giving you this vector r, which is the pencil that is sketching out the line. And this pencil moves and elongates and shortens in order to draw this line. And so here's an illustration of that. So think of the red vector here, and you can kind of see where it's at. See how y equals 0 is there, z equals 0 is there, x equals 0 is there. So this is the origin right down here. Okay, so that is our r that we're producing. And so the idea is, as I put in different values of t, it changes the direction of r, it changes the length of r, and I like to think of letting t be different things basically allows this r vector to draw the line that we're trying to draw. So the equation is literally giving you the kind of, it's like a magic pencil that changes length, changes direction, and as it does so, the tip of it draws out your line. All right, so down below here, here's what I already actually wrote up there. So first of all, here written out is your vector equation, x0, y0, z0 plus t times abc, where abc is the direction vector. You can kind of think of the direction vector kind of like you think of slope, you know, in your past experience. The parametric equation for the line, so this would be just me listing out the x, the y, and the z separately, but it's the same information. All right, so let's do one example here. It says find a vector equation and parametric equations for the line that passes through the point 1, 3, 4 and is parallel to the vector 3, negative 2k, or 3i, negative 2j plus k. So this point here, if it passes through this point, here's what we can do. We can take this point and we can say R0 is equal to 1, 3, 4. And then if we want to be parallel to this, parallel to that means that's our direction vector, right? Look, go back and look at the diagram, right? The line is always parallel to whatever the direction vector is. So that is going to be our direction vector. So we'll say V is equal to 3, negative 2, 1. So writing out the vector equation would be to say r, and it's a function of t, is equal to 1, 3, 4, right? That's r0, plus t times 3, negative 2, 1. There's our v. And to put it together, 1 plus 3t, 3 minus 2t, and then 4 plus t. So there's our vector equation, and then parametric equations are just me writing out each one separately. So there's our two different representations here. So that's our vector equation. And these are our parametric equations. All right, now there's one other way that we can express the equation of our line, and that is through the symmetric equations of the line. Okay, so if you take your parametric equations and just kind of jot this over here. So you take your parametric equations, x equals x0 plus at, then you can solve for t. So x minus x0 equals over a equals t. But you know what? If you started off with y equals y0 plus bt, you could do the same thing for this t. So I don't need to do it again, I don't think. But I think you'll believe that that can be written as y minus y0 over b. And then with z minus z0 over c should be t. So all three of these are all equal to the same t. And so that must mean they're all equal to each other. So this is called the symmetric equations for a particular line. Okay, so example 2 then says find a vector equation, parametric equations, and symmetric equations for the line that passes through these 2 points. Okay, so here's one of those situations where it's good to make a little sketch, but don't worry too much about trying to put it actually on a graph or anything. Just kind of try to represent this idea that you know that you want it to pass through these 2 points. Don't worry about the accuracy of this. Okay, so let's think about how do we come up with the equation for this. Okay, so remember what we're looking for, right? Right, on our diagram on the previous page, right? We need an R0 and we need a V. Okay, so and again, I'm not trying to be accurate, but let's just pretend like this is the origin here, right? Here's the origin. So the idea is I need to have an initial vector that goes to one of these points. So that's going to be my R0. And then I also need a direction vector that is parallel to these, right? That would be my V. But as you can see, I know how, right, to make a vector if I know 2 points, right? I just subtract these. And then R0, if it's starting at the origin, I can just express R0 as being 4, 10, negative 6. And then, of course, V can be 7 minus 4, 9 minus 10, 2 minus negative 6, right? Just subtracting these points, x, y, and z values. So my direction vector then is 3, negative 1, 8. And so that's enough just right there. So I can say that R of t is going to equal 4, 10, negative 6 plus t times 3, negative 1, 8. Or if you'd prefer it as just a single vector, 4 plus 3t, 10 minus t, negative 6 plus 8t. So there's our vector equation. All right, give myself a little more space here. And then, of course, the parametric equations are pretty straightforward because it's just taking these but writing them out as x equals, y equals, and z equals. So x equals 4 plus 3t, y equals 10 minus t, and z equals negative 6 plus, that's right, that's supposed to be a plus there, plus 8t. So there's our parametric equations. And then our symmetric equations. So remember that is going to be just x minus your initial x value divided by the x component of the direction vector is equal to y minus the initial y value divided by, in this case, negative 1, because that's the y component of the direction vector. And then z minus negative 6, I'll go ahead and put plus 6 divided by 8. So those are our symmetric equations that get across the same information. All right, now one trick, and this is a really handy trick, especially I really recommend this, especially just to kind of log away in your mind for Calc 4. This will be something that you will use a fair amount in Calc 4, and that is if you want a line segment only, okay, just a line segment that goes between 2 points, okay, or I guess you could say goes between 2 vectors, then what you can always do is take 1 minus t times the initial vector plus t times the terminal point vector. So here's what I mean by that. If here is a point and here is a point, you know, and this is R0 and this is R1, then I know I can make a line that goes through there, but let's suppose I only want a line segment. I want the line to start here and end there and go no further. The way you do that is like this. And the reason is because, and if you only let t go from 0 to 1, then when t is 0, then what you're going to have is 1 times R0 plus 0 times R1, right? So you're going to have none of R1 and all of R0. And then when you get to 1 at the end, that's when you're going to have 0 R0 and 1 R1. So then you have only this at the end. And so by letting t go between 0 and 1 and setting up the equation this way, that ensures that you just have a segment that begins at R0 and ends at R1. All right. So let's, in example 3, it says find where your line from example 2 intersects the xy plane. Okay, so the line we were just talking about, so let me just write down the equation again. I'll just write down the vector equation is fine. So r of t is equal to 4 plus 3t, 10 minus t, and negative 6 plus 8t. All right, so let's think about what do we know about the xy plane? Is there anything special we know about it? Well, the xy plane is the place where z equals 0, right? So if z is equal to 0, we can set z equal to 0, which means we take the z component, set it equal to 0. So 8t equals 6, t equals 6 over 8, so t is 3/4. So what that tells me is that t, our parameter value, must equal 3/4 at the moment when z equals 0. So then we can take our x component and say, okay, well, what does our x component equal when, oops, sorry. So 3 times 3/4. So I'm just plugging that t value in for my x and 3/4 in for the t value and my y component as well. So x equals, I'm going to need a common denominator, so this will be 16/4 plus 9/4. So x equals 25/4. And then y equals 40/4 minus 3/4. So y equals 37/4. So with all that, and I kind of ran out of room, but where does your line intersect the xy plane? It would be at the point 25/4, 37/4, 0. All right, so in example 4, it asks us to find a vector equation, um, parametric equations, and symmetric equations for the line that passes through those 2 points. All right, so here's where what I would suggest is to use what we learned on the previous page. So, and now as I'm doing this example, I'm not sure why I didn't make this example 3 and follow up the previous page with that, but oh well, I'm not going to change it now. So back here, what did we say? We know how to make a line that goes between 2 points by setting it up this way. We can do the same thing here, right? So we can kind of think of this first one as our R0, and we can think of this point as representing our R1. I know this is a point, not a vector, right? But our vector can be the arrow going from 0, 0, 0 to 5, 3, 1. And use this, right? R of t equals 1 minus t times R0 plus t times R1. Now, on the previous slide, the thing that made it only go from R0 to R1 was because we only let t go from 0 to 1. But if we let t be whatever it wants, then we'll get a full line that goes wherever it wants. So here we're just not going to put that restriction on it, but we'll still use this same formula. All right, so I can say R of t is equal to 1 minus t times 5, 3, 1 plus t times 2, 1, 1. All right, and so as I do this, we'll end up with 5 times 1 minus t, 3 times 1 minus t, 1 times 1 minus t, that's the first vector, plus 2t, t, and t. So here it's 5 minus 5t, 3 minus 3t, 1 minus t, plus 2t, t, t. And then we can put those together. So 5 minus 3t, 3 minus 2t, and then just plain old 1 there at the end. All right, so there is our vector equation. Okay, so then our parametric equations are x equals 5 minus 3t, y equals 3 minus 2t, z equals 1. But how about our symmetric equations? Okay, this might be kind of awkward because we're used to taking our symmetric equations and saying, okay, well, let's take, x minus some initial x value, which I'll say is 5, over the negative 3 is equal to y minus 3 over negative 2. But then there is no direction vector component for z, right? Because it's just 1 here. So if that ever happens to you, then your symmetric equations are going to be just these two with the extra statement by itself, z equals 1. Okay, so I wanted to show that example, so if you ever run into that, you know how to deal with it. All right, so we used this nice little trick at the beginning. Earlier we did an example where we found the line that went through 2 points, and we did it differently, remember? Remember, we found a direction vector first and then picked one of them to be our initial vector. So can we just agree here that everything would have turned out exactly the same? If I was going to find my direction vector v, I would have said something like 2 minus 5, 1 minus 3, 1 minus 1, which is negative 3, negative 2, 0. And those are the exact A and B that I actually ended up with, right? So this is just a different way of getting at the same thing, and you can decide if that's the way you want to go about a problem like this.